Okay, welcome again to this video lectures on LP with SPICE, linear programming with SPICE for the operations research. And what has happened so far, we have built out an LP for the Nutient problem. Let's recall the Nutient problem. So we have a seed stubber Nutient problem. So seed stubber needs this amount of nutrients and wants to buy these nutrients from more deep bakery. So basically the amount of nutrients is the same as the amount that's needed is the same as is or the more deep bakery has. So now this is balanced in such a case. And we are not buying the cakes, we are buying the nutrients. And it turned out that that's 6.12 is the LP we have. So we have to decide how much we are going to pay for each nutrient, and then we have to minimize. So this is the how much we then buy. We buy exactly the amount we need. So that's the requirement, nutrient requirement. And then we have a constraints as lower bounds now, not upper bounds, because these tells us that these three lines tells us or ensures that our offer for more deep bakery is better than what they could do themselves. So this was the LP. In some sense we are finished then it's just a matter of solving this with CLPK, and this is actually left for you as an exercise. So in this short final video lecture on this chapter, there are just some remarks, or one remark. And this is a very important remark, this 6.13, in the sense that this is explained that we have now actually seen our first duality, true duality. And we will have later an entire chapter about duality. That chapter will be somehow, or I keep it more theoretical there, so we don't have so much these funny examples based on the Dune universe. So let us, to prepare for that, let us a little bit see what did happen here. So we have seen our first duality, and one way of looking at it, what happened here is, again, you have seen this table many times. Maybe this is the last time. Maybe I will copy paste this table still somewhere. So this is the more deep table. If you just look at this table, we have something Fremen cake type. So we have an inputs, if you wish, or raw ingredients that are turned into products. So ingredients are these powders and products are these different types of Fremen cakes. Here is a technology matrix that tells us how this is done. Then we have an availability. So how much do we have these raw material ingredients, and then we have a selling price here. Okay. So whenever we have a table like this, then I mean in the LP setting, and especially if we want to solve it with GNU Octave, we would like to, or it's an obvious thing or natural thing to represent this stuff here as with vectors and matrices. So C is a column vector, which is here telling the selling prices. A is a technology matrix that tells how the nutrients or raw materials are turned into products. That's the technology matrix A, numbers here. And finally we have the availability of the how many resources we have, and in the dual case that's the requirement, how much we need. It's given here. And now note that I have done the unit change here. So now everything is in the same units. So formally or schematically, the mod dip is looking this kind of table. Now I've just removed here that there are traders Corino, Harkonnen, or Nutrients, what they are called. I mean, when we are formally solving it, we don't care what they actually are. Let's do at least this little bit of abstraction here. So it means that we are looking at, in a schematical or formal sense, this kind of table, and the way to read this table now we are reading it a product mix sense. So we are reading is the selling, how do you sell things. So it's a maximization. So this kind of table, whenever you have, and you can interpret it or consider it as a product mix problem, it will be like this. So we maximize objective, which is given by this, and we have a constraint that this A here cannot exceed the availability or how much we have these raw material things we are turning into other things. So this kind of table, at least when I see it and it looks like a maximization, then I kind of automatically interpret it this way. So this stuff here is this stuff. Okay, that was the product mix. That was the mod dip bakery way of thinking. Now what is the dual way of thinking? And then we, if you wish, we don't read this row-wise, but column-wise. I mean, whatever that means. It's not even clear to me. What does it mean reading row-wise or column-wise? And that's kind of an important thing to understand, that it's the same thing, but a different point of views. But if I want to make, especially with this, to say that this is something that we, instead of reading it like rows, we read it like columns, or the other way around. What do? You switch rows and columns. That is, in linear algebra, you call this transposing things. So now this here transposed is here. Sorry about this painting. Let's see if now they are both shown. Maybe I make this slightly smaller so it's easier to see them both. I hope this is not going to make the font too small. Yes, here you have it. So this is the table how you would read the mod dip problem, and since we are looking at duality, so let's call this primal. So there's a pairing, there's a primal, and then there's a dual. So that's the primal. And I make this even smaller, so I hope that now, although the text, so this is an optimization problem again, I'm not sure whether it's linear or not, to make, so you can see more, but then you have to, maybe the text is too small, so you don't make out the details. But maybe it's not so important to look at the details too closely here. So here we have A is a technology, and there is an upper bound how much we have say inputs or raw materials, and then here we have the products or the outputs, and this gives us selling price. So the transpose there is just that it's a row matrix, row vector now. Okay, now if I take the table and rotate it and maybe flip something, so basically I change rows and columns. So this is just the formally the same thing, but now I look from the type that there is I want nutrient powders or the nutrients, and there are different Fremen cake types that gives me somehow restrictions on them, and they give restrictions related to the selling prices. So I have to offer prices for the nutrients so that they are bigger than the selling prices, because otherwise, I mean, why would Muad'Dib Bakery accept this offer? So this C prime goes here, C, again the prime goes away, or it's prime prime, which is just does nothing. And then kind of the objective, because here it's the requirements. So the requirements that I need are exactly the availability that they have. So this is the balancing thing here. And then if I have this kind of problem, I mean formally it's more or less like this, but now it's a minimization. Okay, note that this here A is transposed because I changed rows and columns. So it's a minimization, or W B prime now here times Y, subject to constraints that A now prime Y, and here this is not less than equal because it's a minimization, it's bigger than equal to C, and yes, they both have sign constraints. So this is what's later, well, let's call it already, this is called a duality. So this is the primal problem and this is a dual problem. So Muad'Dib's bakery problem was a product mix problem, and that was our primal problem where we started, and then it's dual problem, which formally just goes like this. You change rows into columns and change maximization to minimization and upper bound to lower bound. This is the dual problem. Okay. And now we actually end this section here just by giving you an exercise. So what happened here now is that we modeled the dual problem. So the nutrient problem is modeled, and we have also told a little bit about duality and so how it is actually a dual of this Muad'Dib Bakery product mix problem. And 6.14, I really wanted to leave this as an exercise for you because this deals with central topics, so it's much better for you to do it yourself than just to watch videos. So solve this nutrient diet problem 6.8 by using GLPK, and then compare the solution with the Muad'Dib Bakery product mix problem, and actually it's solution 5.7. So let us shortly here in the end look at the 5.7. So this is the Muad'Dib Bakery revisited. Here is the link for this code. You can use this or the link for this without this revisited. And yes, in solving this exercise, you can start from scratch, or if you are clever enough, you can maybe use this as a basis, or you can use the not Muad'Dib revisited but Muad'Dib.m, since you can see they are closely related. So the data is as you can see in the Muad'Dib, the data was A, okay, C, A, and B. So they are here also almost the same, but of course the C turns out C will be B and B is C and A is A transpose. Okay, there are many ways of solving this, either from scratch or by somehow copy pasting and using the primal problem. But this is an exercise for you. And that was all of the chapter 6. So diet problem and nutrient problem. and in the next video lectures something completely, well, not completely, but slightly different. Bye bye.